Hi, I'm Pat and I'm the MCAV software lead, and welcome to our project showcase video for 2020. At the start of the year, we began work on our new vehicle, the street drone, and quickly brought it up to the level of last year's demo. From there, we expanded our testing onto the car parks on campus. Unfortunately, after COVID, we weren't able to do any more testing on the vehicle and began working from home and moved all our development into simulation. From there, we focused on two main goals. The first being to reduce our reliance on HD maps, which allows us to drive in a wider variety of scenarios, and the second, to move away from AutoWare, which is a library that we previously relied on extensively. This resulted in us having to develop a lot more of the system by ourselves. In this video, you'll hear from some members of our team about the projects that they've worked on this year.
Hi, my name is Minsu and I'm part of the object detection subsection, and I'll be discussing about the lane detection system. The MCAV lane detection system uses the camera information attached to the vehicle to identify the drivable areas on the road. This involves recognizing the lane which the vehicle is currently in, as well as lane which the vehicle can possibly move into. The detection system is a subset of supervised machine learning, which is defined as image segmentation. This processes the camera feed to a fully convolutional neural network pipeline and classifies each pixel into one of three different categories: drivable, alternative, and none. The results from the drivable lane detection systems were utilized by other key projects MCAV have been working on. One particular use of our lane detection system is that it provides information to our path planning system by transforming output detection to a cost map. This also involved taking the output detection and projecting it to the 3D space, which then allows paths to be dynamically planned without requiring predefined boundaries.
Object detection allows the vehicle to locate and identify typical road obstacles. It is the integral first step in ensuring the vehicle reacts appropriately and timely to objects such as traffic signs, pedestrians, and vehicles, and avoid road accidents. MCAV is currently experimenting with YOLO object detection models, which are optimized for real-time detections. Specifically, we have trained YOLO version 3 on the Berkeley Deep Drive dataset and compared it with the default weights used by AutoWare, which were trained on the COCO dataset. The team is also aiming to classify and locate objects in 3 dimensions. Our plan is to take the 2D object detection information and match it with the 3D Euclidean clusters from the LiDAR. Currently, we're at the stage of rectifying the LiDAR point cloud in a way which allows us to find the 3D coordinates of the classified objects.
Depth estimation is used to perceive the distance to objects from the vehicle. This can be used to enhance perception systems to determine where the vehicle is and what is around it. The team tackled 2 different approaches to estimate depth with a single camera, which predicts the depth of every pixel in a given image to try to minimize the sensors required for perception. The first used a neural network, written based on literature and trained on the KITTI dataset, a large outdoor dataset with RGB images and projected LiDAR data, which acted as ground truth. Transfer learning was then conducted with the team's recorded data. Due to inaccurate sensor calibration and data collection techniques at the time, there was misalignment between the ground truth data and camera images, and recording new data was not possible due to COVID-19 restrictions. Predictions from the depth neural network were utilized to optimize camera calibration parameters. This introduced a self-correcting system to fine-tune the depth neural network despite having an initially misaligned dataset. Motion compensation and time synchronization were also addressed to improve alignment. The second approach used an open source depth estimation algorithm named big to small and experimented with projecting the depth map back into a 3D point cloud using a method called pseudo-lidar. This aids in creating dense point clouds for object detection algorithms and further reduces the need for a lidar.
Hi, my name is Owen and I'm part of the path planning subsection of the software team at MCAV. 2020 has seen the creation of a new path planning pipeline. It divides the driving task into two main subtasks, following the current lane and crossing an intersection. The lane keeping system is responsible for control of the vehicle during most of the driving. However, when the vehicle approaches an intersection, as determined by pre-marked locations on a large static map, an algorithm known as hybrid state A* is used to generate a path from one side of the intersection to the other. Once generated, the path is handed over to the pure pursuit package built by the controls team. The hybrid state A* algorithm is an extension to the widely used A* search algorithm, known for being efficient for finding the shortest path between points on a map. The hybrid state extension to this algorithm modifies it to better take into account the dynamics of the vehicle, particularly with regard to steering.
Hi, my name is James Selbank and I'm the Track and Control Lead here at MCAV. This year we had three main projects. We had the CAN interface, the MCAV Manager, and finally the vehicle controller. The CAN interface was one of the first projects to be completed in the year and was required to communicate with the street drone's internal systems. It can read data ranging from whether the headlights are active to what autonomous state the vehicle is currently in. It's a ROS node that subscribes to received messages and publishes the topic for each CAN message in SD state messages. In creating the interface, we needed to interpret a giant database of CAN messages with their corresponding IDs. This proved a challenge, but in the end, we now have a system that can read any new CAN database if any signals are added and incorporates them into the interface CAN readout automatically. MCAV Manager is a complete solution to running the code that MCAV has created throughout the year. It communicates clearly to the user about what nodes are running, whether they are healthy, and what state the vehicle is in. In practice, it allows the user to change states and prevents contradictory nodes overriding each other by silencing those that are not currently used. Control is the way in which the vehicle reacts to its surroundings and the target waypoints given by the planner. It's an integral part of any system, especially that of an autonomous vehicle, where any malfunctions in incorrectly following the path could result in catastrophe. This year it was decided that Pure Pursuit from AutoWare would be used again, as it was with last year's demo. A few changes needed to be made so that it would interpret the new message types passed from MCAV Planner, as well as the fact that it now had to interact with a simulation rather than a physical car. Pure Pursuit itself works by taking a set of waypoints and interpolating between the current and next waypoint. It then solves for the unit vector parallel to this line and creates a new target point based on a given look-ahead distance. Finally, the radius of curvature is found and a given angle theta for steering angle is then published.
We've created an app to visualize and explore the large amounts of data produced by the car. This allows any engineer to load up a recording and visualize any of the data streams. They can view this data in aggregate or over time and along with any of the other variables. This is useful for understanding how the car is performing or debugging any problems with sensors or systems. The app also includes all the images from camera feeds, so it can be used in the development of neural networks. For example, if our object detection team wants to improve the performance on traffic lights, they can load up all the data, filter to only images of traffic lights, extract these images, label them, and then include them in the next training run.
Hello, I'm Collier and I'm Chief Engineer. So for demonstration purposes, we have developed an Android tablet app to provide a user-friendly interface that non-technical users can easily use. This is called the tablet interface. It was initially prototyped in 2019 and further developed this year. Its basic function is to allow the user to start and stop the vehicle, select the destination, and provide useful information about the state of the vehicle to the user. The tablet can be used easily to showcase our ability to actuate vehicle controls at the push of a button, at open days and other such events. The tablet communicates via Bluetooth to a Raspberry Pi that is mounted on the vehicle and is connected to the ROS network. Since the tablet-to-vehicle communication is wireless, the tablet can be used inside of the vehicle during tests or to show the state of the vehicle during tests to watchers at a base station.
Hello, my name is Surya, and I am currently part of MCAV's software section with a focus on perception-based systems. So the main idea of a new lane keeping system is that it utilizes information provided by our lane detection system to help keep a vehicle within its current lane. Many vehicles today come with this driver assistance feature, and it's most effective for roads that have long, uninterrupted stretches like highways. Getting a little more into how it works, by first using our lane detection model's output, the lane keeping system first finds how far from the center lane the vehicle is. This information, which is distance, is then fed back into a PID controller, which outputs a steering angle to shift the car back to its lane center. This was an important feature to develop as we find that the fundamentals that make up autonomous driving are made up of many driver assistance features, such as this one. So by being able to first autonomously keep a car within its lane, we can move on to building more complex features, such as keeping vehicles between cars within the lane, or even implementing a lane changing or emerging system. Due to COVID reasons, we did have to develop everything and test everything within the simulated environment. However, because of the flexibility of the software we're working with, we should be able to translate everything we've done in simulation this year to real life on the street road, which we aim to do once we get back on campus.
You know, it's been a tough year on everyone. I'm incredibly proud of what we've been able to do this year, and just like to thank the team for all their hard work this year. We're looking forward to getting back to the real world and seeing each other all again next year. Thanks for watching.